On 4th November 2010, Qantas Flight 32 took off from Singapore Changi Airport, bound for Sydney. Minutes later, that calm was shattered. The number 2 engine suffered an uncontained failure, sending high-energy fragments through the left wing and damaging multiple aircraft systems. In the cockpit, Captain Richard de Crespigny and his team of 4 other pilots were suddenly faced with one of the most complex emergencies in aviation history. Yet, through calm leadership, teamwork, and extraordinary focus, they guided the crippled Airbus A380 and brought all 469 people on board safely back to Singapore. I'm Richard Godfrey. Welcome to Independent Aircraft Investigations. QF32 was not simply a story of checklist discipline. It was a story of disciplined doubt. The ATSB found that the aircraft remained capable of continued safe flight and landing, despite significant damage, and that the flight and cabin crew managed the event effectively in accordance with procedures and practices. The ATSB found that a non-conforming oil feed stub pipe in the number 2 Rolls-Royce Trent 900 engine led to fatigue cracking, oil release, an internal oil fire, turbine disc separation, and an uncontained disc burst. The report also explicitly identifies the safety message: clear manufacturing procedures, compliance with those procedures, and better incorporation of uncontained engine rotor failure, UERF, lessons in certification guidance. The ECAM sequence should not be read as 116 independent aircraft failures. 46 of the messages were repeats, and some were likely the result of severed wiring and damaged sensors or corrupted signal paths after the uncontained engine failure. The prime airborne performance degradation came from 3 sources: the loss of number 2 engine thrust, damage to the left wing, and damage to wiring and system interconnections. Fuel was leaking, but not at a rate that immediately threatened continued flight. Hydraulic and electrical systems were damaged, but sufficient redundancy remained for the aircraft to be controlled and landed. The prime landing performance degradation was different. By the time the aircraft returned to Singapore, the major concerns were the overweight landing, degraded or uncertain speed information, braking and steering capability after touchdown, and the continuing fire risk from leaking fuel. Touchdown, therefore, did not end the emergency. It changed its character from an airborne control and diagnosis problem into a landing, stopping, fire risk, and disembarkation problem. On the 1st of November 2025, I interviewed the captain of QF32, Richard de Crespigny, known as Rich, together with my colleague Geoffrey Thomas from Daily Airline News. I asked Rich what it felt like in the cockpit when the aircraft was still flying, but many of the messages and sensors and checklists could no longer be taken at face value. This is what he had to say.
Hi, Richard. It's 15 years ago now, and I still remember the events just like it was yesterday or even now, because the engine exploded and broken into many pieces. Those pieces energized shrapnel, and they broke about 650 wires. They cut about half the network cables. 21 out of 22 systems were affected. And interestingly, on all these aircraft, if you get away from the internal Airbus technology, you start to use a thing called CAN, or CAN bus, made by Bosch, in their cars to communicate to engines and different parts of the airframe that are made by someone else. And parts of the problem with the CAN bus is that it's only a two-wire network. So if you break a wire, you might sever the connection to the sensor. There are 250,000 sensors and parameters on the A380. But when all those wires were cut, we lost a lot of CAN bus connections. So a lot of these, we received a lot of checklists, 100 checklists we were told to do in the air. The aircraft had also sent 160 messages to Airbus in Toulouse, Rolls-Royce in Derby, and Qantas in Sydney. But we were faced with 100 checklists, and the first thing you do is you never just accept anything by itself. You always have to confirm any message, because computers and sensors can be wrong, and you never have a single source of failure. So everything must be confirmed. The problem was that because a lot of the sensors coming off the engines were using CAN bus, and the CAN bus connections were damaged, a lot of the indications we got on the aircraft, when we tried to confirm with a synoptic panel or with like a schematic of the aircraft that we were presented with in the cockpit, a lot of the indications that we got, we later found out that they were wrong. So the checklist that we were given in many cases were either marginal or wrong, and we had to use all our knowledge, training, and experience to confirm what was broken. And if the evidence suggested that it was broken, we actioned the checklist. If the evidence suggested maybe we shouldn't do it, and that would happen with the hydraulic system, because they wanted us to turn off hydraulics on the right-hand side of the aircraft, even though the engine had exploded on the left-hand side of the aircraft. It made no sense to us when you have separate hydraulics, why we were getting those sort of checklists to do. So we questioned every checklist. Some we did, some we instantly, some we questioned and we did. And there were many checklists that we queried and we didn't do them. And there was exactly the right decision, because the sensors were either broken or the checklists were incorrect. And I did receive a letter from Tom Enders, who was the CEO of Airbus at the time. He said, "I apologize for ECAM, but well done on working your way through the problems despite the errors in the sensors and the ECAM. You resolved all the right problems and you got everyone else home." And so there are problems with the indications, both for the electrics, the hydraulics, the fuel system. That was a mess. But this whole QF32 story is not about me. It's about the team. And the team, we pulled our brains into a super Borg type brain from Star Trek. And we combined all our knowledge, training, and experience. We resolved all these issues. We worked through, we knew that aircraft down to its half ball valves and electrons almost. And I'm really proud that all the decisions we made that day were correct. All the checklists we did, I think, were correct. All the checklists that we ignored, we needed to ignore. And mind you, that is a stress for people in other airlines. Pilots in other airlines say, well, of course, you must always follow the checklist because Airbus produced that. It's made by the experts. But, sometimes those checklists were written by computer science graduates, come out of university, never been into an aircraft. Sometimes those checklists are wrong. Pilots have to have chronic unease for the status quo. You're skeptical of everything. You need proof for everything. We face the enemy in front. We ignore what's behind us. You find facts and you run facts to 10 decimal places. And if everything matches, that's fine. And if it doesn't, you ignore it as noise. And so I'm sorry that's such a long answer to the question about the faulty ECAM. But when you know your aircraft down to not just the core, but to the foundations, you know how to turn computers off if they're faulty. You know how to determine if they're faulty. You know how to ignore checklists if they're not going to help you. This is an advanced skill that comes when you have a wonderful team of pilots we had in the flight deck working together. We resolved all those problems to a happy ending.
For de Crespigny, the experience was life-changing. His name became synonymous with cool-headed professionalism. But the story of QF32 is also deeply human, and of a crew who refused to let chaos win. In the years since, de Crespigny has devoted himself to sharing those lessons beyond aviation, exploring how resilience, decision making, and emotional intelligence can help anyone navigate crisis. In this conversation, Rich reflects on the moments that defined that unforgettable flight, what it taught him about resilience, and why staying calm under pressure is something that can only be learned. 15 years on, his insights remind us that while technology keeps evolving, it's fragile. Rich said, I've seen 5 engine failures in my whole career. Now, curiously, he says, the engines only fail one in every 350,000 engine hours. Most pilots never see an engine failure, and I've seen 5. I've seen enough failures, and I don't get as surprised. Rich continued, there were 2 loud explosions. The second one was very loud, and the aircraft shook. And then the alarms went off, and the alarms went continuously for 30 seconds. Matt's trying to cancel them. They kept coming back. I was trying to cancel them. They wouldn't stop. There's red lights. There's ECAM checklists flooding up. There's so many distractions and certainly a lot of opportunity to put us into the fear response. His point is not that experience eliminates fear. It is that realistic practice builds habits strong enough to survive surprise, noise, alarms, and overload. Let's have a look at the teamwork in the cockpit. The team structure, we had 3 captains, and we had a first officer and a second officer. Rich recounts on the way out in the bus to the airport, I said to the other 2 pilots, because my crew was a team of 3, but I was being route checked by Harry and Dave. There are the 2 other captains. Harry was learning to be a check captain. So we had David Evans, a very experienced captain, training Harry to be a check captain. And we had a check captain training a check captain to check me. The first key issue was stabilizing the aircraft. Rich focused on aviate, navigate, communicate. He says, so I pressed the altitude hold button habitually to lower the nose to cause the engine thrust to come off, but it didn't. I press a heading hold to stop the aircraft following a curved departure. I watch the speed, and bearing in mind at this time, no one else is saying a thing. Everyone's quiet. No one is panicking. No one's in the fear response. I think, and then I watch the speed. The speed's increasing. We're about to go into overspeed. I don't know why, but I grab the thrust levers and I pull them back to idle. I take manual control of the aircraft. And then after about 30 seconds, I called out the first words that came on the flight deck. We are at a constant altitude, a constant heading, and we are above the hills. Our speed is constant. We are safe. ECAM actions. The next part was regaining situational awareness. When we're trying to follow all the primary failures and anticipate the secondary failures or knock-on effects, I lost my situational awareness. And at that point, I made a request. In fact, I didn't tell the other pilots. I said, Air traffic control 32 require a climb to 10,000 feet and keep us inside 35. Keep us inside 30 miles. Now, there was that deliberate call because I wanted to get the aircraft to a safe height where I could glide back to Singapore if we lost all engines. The second thing I did was invert the logic. Instead of looking things that failed, I looked at what we had left. An Airbus A380 has 4 million parts. It's a $400 million airplane. It has 1,200 checklists. To explain that mental shift, Rich reached for an analogy from Apollo 13. Gene Kranz was a mission controller in Houston, and Gene Kranz stood up during the Apollo 13 crisis when the controllers were breaking down over the overload of sensory data coming back from Apollo 13 spacecraft. And Gene yelled out, "Stop wondering about what's failed and focus on what's working." This is inverting the logic. So, what was the QF32 mental model? It was focus on what you have. Rich says all we needed to do was to get enough wings, enough brakes, enough electrics. We're doing a junkyard wars build of an aircraft from the ground up. Do we have enough of these things? Focus on what you have. And when I did that, everything became understandable, manageable, and I regained my sense of calm and my whole mood changed. And now I got my situation awareness back. And I looked at the aircraft from the reverse concept. Instead of having 8 fuel tanks out of 11 that had failed, all I needed to know, we had 3 fuel tanks sitting over the 3 engines that were running, and we had enough fuel. We didn't need the fuel pumps. We could transfer the galleys from the electrical power. We didn't need the fuel computers. And that was a really severe change in mindset that made this crisis simple. Rich has been outspoken on the subject of automation and the gradual erosion of manual aircraft handling skills. So, what is his recommendation for the modern flight deck and modern pilot training? The lesson is not to reject automation. It is to remain capable when automation is unavailable or misleading or no longer appropriate. Rich said, whenever I took off and the conditions were suitable, in other words, it's not busy and the airspace permits it, I would fly manually to 20,000 feet on every takeoff. And I would fly manually down from 10,000 feet to the ground on landing. I would fly at every opportunity. I would only use the automatics if I had to. I would go into the simulator and I'd say to the instructor, once I pass my simulator check, I want you to knock up the crosswind to the maximum limit for the aircraft. And then when we get that, I want you to put on maximum turbulence. And when we get that, I want you to turn off the flight directors to make the approach as hard as possible. I have to challenge myself. The whole point in doing this, in doing these hard things that stress you, that are uncomfortable, you're building up confidence to be courageous, to be fearless, that when you turn off these computers, you're not afraid to fly the aircraft. The direct technical failure was small, a thin wall section in an oil feed stub pipe. The consequence, however, was not small. Oil escaped, an internal fire developed, the intermediate pressure turbine disc separated and burst through the engine casing. The systemic lesson is that catastrophic failures can begin as ordinary process failures, unclear instructions, weak non-conformance control, and missed opportunities to detect a part that did not meet design specification. As a result, the ATSB issued recommendations to the European Aviation Safety Agency and the US Federal Aviation Administration, recommending that both organizations review the damage sustained by the aircraft in order to incorporate any lessons learned from this accident into the certification compliance advisory material. The aircraft sustained significant impact damage to the left wing by fragments and debris from the UERF, and fuel was leaking from the damaged left wing fuel tanks. However, after completing the ECAM procedures and performing some aircraft controllability checks, the flight crew landed the aircraft safely at Singapore Airport. The emergency was not over at touchdown. The crew still had to decide whether an evacuation would reduce risk or create a greater one. After landing, fuel continued to leak from the left wing tank. The risk associated with this leak was minimized by the airport emergency services, who applied large quantities of water and foam below the left wing as the crew worked through the shutdown problem. The number one outer left engine continued to run, following the normal shutdown procedure. Because of the still running engine and leaking fuel on the left side, the passengers were disembarked via a set of stairs on the right side of the aircraft. The flight crew elected to use a single door for the disembarkation so that the passengers could be accounted for as they left the aircraft, and to keep the remainder on the right side of the aircraft clear in case of the need to deploy the escape slides. They also decided to leave the remaining doors armed, with cabin crew members at those doors ready to activate the respective escape slides until all the passengers were off the aircraft. The disembarkation was completed about 2 hours after the aircraft landed. Numerous unsuccessful attempts to shut down the number one engine were made by the flight crew and by maintenance engineers and the airport emergency services using different methods. The engine was finally shut down about 3 hours after the aircraft landed by pumping firefighting foam directly into the engine inlet. The two lasting safety lessons are these. When automation and systems degrade in complex ways, the crew's job becomes management of uncertainty, not merely checklist execution. The QF32 diagnosed, preserved options, avoided rushing the return, assessed controllability, calculated landing performance, and chose a precautionary disembarkation rather than an evacuation into a potentially hazardous external environment. The second lasting safety lesson from QF32 is that rare catastrophic failures can be born from ordinary process failures, unclear manufacturing instructions, weak non-conformance control, missed inspection opportunities, and informal assumptions about what is minor. In QF32, the A380 survived an engine explosion, not because the initiating failure was small. It was an uncontained engine rotor failure with major structural and system damage, but because of multiple layers that still held: aircraft damage tolerance, crew discipline, cockpit resource management, ECAM handling, conservative decision-making, and emergency response. QF32 was not simply a story of checklist discipline. It was a story of disciplined doubt. Thank you for watching. If you found this analysis helpful, please subscribe for future investigations. Next week, we will take a look at Qantas Flight 72. I look forward to your company as we continue investigating the lessons that can make aviation safer for everyone.